Do people have particular questions about what will be? Does anybody have particular? Or do you just want me to go over the practice exam? All right. Until someone has a question. Oh God. This is going to be obnoxious. Okay. Professor Weening says he already did number 1 with you guys. So, for the most part, does anybody want to do it again? No. Okay. I got 1 no, and that's it. No other responses, so we're going to not do 1. Go straight to 2. Okay. This is obnoxious. Okay. F is 4x cubed. Part A says find partial f, partial x, and partial f, partial y. Can everybody do this? I hope. This is the easy part of the question. Who wants to do it? Anybody?
Sure.
Sure, you do it.
All right, so you would have, for the partial x, would be 12x squared y plus y squared. And then for the partial y, you would have 4x cubed plus 2yx.
Okay. Now, find the equation of the tangent plane at 1, 2, 12. So who knows how to find a tangent plane? It is probably much easier than you think. It's much easier than I thought it was. The equation for the tangent plane is just z minus z naught. It's not a very hard formula, and now you can just plug in numbers, which is great. So what is z naught?
Should it be the 12 in the point that you're trying to find the tangent?
Yes. Z minus 12. Let me see if I can. Zoom in. That's not what I wanted to do. Oh, this is awful. Whatever. I'll deal with it. Yeah, z minus 12. And we want f sub x at this point. So we plug in 1, 2. So we get 12 times 2 plus. So that's 28. must mean somebody asked a question.
Oh no. It's all good.
20.
If you press both of the buttons, then yeah.
The two buttons at the where the markers are being held, will be pressed at the same time.
Hold up.
Yeah, you can then click.
Now, what this mess is, I'm going to write it here. Z, much better. Z minus 12 equals 28 times x minus x naught, which is anyone? X minus 1. X naught is 1 plus f sub y at 1, 2. So what is that? Plus 4. Comes to y minus 2. That's why not? And if you want to, maybe you should move this 12 to the other side of the equal sign, but that's it. That's the answer. You can simplify all you want. But as long as you know this formula that is illegible now, this one. If you know this formula, hopefully people online can read it, then you're good. Super easy to do that. Any questions about that one? Consider the curve determined by the equation f equals 12. We want to find the tangent line at what point? At 0.12. For f of x, y equals 12. This one is also pretty straightforward. So one thing that might be confusing is we are actually looking for dy dx. We don't have any z's because after we substitute this 12 equals 4x cubed y plus 1 squared x. No z's. So we want dy dx. And we'll just get it implicitly. So the derivative of this we want to take dy dx. So derivative of this with respect to x makes it to the product rule. We'll do x first. Derivative of the first one, the second one, plus the first one. And we'll just keep going with this. Plus the first one. Chain rule. Second one. Plus the first one times the and now we just plug in 1 and 2. Okay. Is there really no way for me to just make this bigger? I guess not. So 4 times, this is 2, so 6 plus dy dx, 4 plus 4, I'm going to write y prime just to save some time, plus 2 times 2 times 1 times y prime, plus so 8y prime equals negative 28. Y prime equals that. That's the slope. Now you use point slope. I don't want to do it, partly because I can't extend the screen, I have to erase it. Everybody knows how to do point slope, right?
Yeah, I just wanted to ask if he uses a different approach on there. Is that also a valid method?
I'm sure it is.
I mean, if that's not
That's what we
a
learned
good one to
in class.
use.
This is what you learned in class?
Yeah, the way he did it, the minus.
Yeah, add another
y.
formula.
Okay. I don't remember that. Sure, let's do it that way. 4x cubed. Copy. Oh God, it's not at all what I want. I was hoping to get in this room early so that I could. I'm just going to erase it. Too much work. Figure what I'm doing. That equals 4x cubed y plus y squared x, right?
Yeah.
I think. Okay. I guess dy dx is apparently negative partial f partial x partial f partial y, which is faster, I guess. And we already got the partials earlier. I don't have them, but you guys should if you're taking notes. So partial f partial x is 12x squared y plus y squared partial f partial y 4x cubed plus 2x. And then you plug in 1 and 2. And I hope we get negative 28 over 8. That'd be good. 12 times 2 plus 4. That's a good start. And 1 plus 2 times 2 is 8. Nice. Okay. Any questions? I guess this is a better way to do it. It's faster. And it uses partial derivatives, which I guess you're practicing for this exam. Sure. What? All right. Great. I can't copy the table
Can you split screen?
onto. Maybe.
Hello. Sorry. Yep.
Okay. Well, okay. What does the second derivative test tell us at each point? I guess I'll write them down.
What is the maximum?
So we want to check. Yeah, yes. It tells us whether it's a max, a min, or a saddle point. In general, this is what we're looking for. Min, max, saddle point. So we do that by checking x, y. No, sorry, y1. So it's fxx, fy, y minus 2 times
No, it's squared.
Squared.
FYX.
xy squared. So just check this guy at every point. So the first one, the point 3, 4, you got 4, 2, 4, 2, 3. So what kind of point is it? We get 12 minus 4.
Greater than 0.
Yeah. So it is a maximum? Minimum? Do we know? Do we know whether it's a maximum?
It says local min.
Could be either. Oh, it's in the house.
If it's positive, then we check. We look at fxx. If this is positive, then it's a local minimum. Okay. Yeah, because this one's a min. Yeah. So this is a min because this guy's positive. Four minus 1. 5 minus 8. What do we get for this guy?
It's negative.
It's going to be some negative number. Yeah, I don't want to compute it. I just know that it's negative. So it's a saddle point. next one. -6, -4, -3. What's weird about this one? What's weird about the 0.23?
Gradient.
Yeah, exactly. The gradient's not 0, the 0.23. It's 0 at all these other ones, but it's not here, which means this thing's not a critical point. So it can't be a minimum or a maximum or a saddle point. So it's not helpful. Or the second derivative test is meaningless at the 0.23 because the gradient's not 0. That make sense? It's like, I mean, it's just like in calculus. If you ask whether something's a minimum and the slope's not 0, it's clearly not a minimum or a maximum. 5, 2, -4, 6. -4, 6. Great. How about this one? -4 times -9 is 36. 6 squared is 36. This one equals 0. What do we know about that point? If this guy is equal to 0. Exactly. Nothing. Questions? I think that's all those questions.
Wait, so the last one's, it doesn't, for 5-2, it's nothing?
Yeah, for 5-2, we don't learn anything.
Okay, and then for 3-4, it's the minimum?
For 3-4, yeah, it's a minimum because the fxx is positive.
Okay.
So that's like, that's kind of like in calculus when you check whether it opens up or down. fxx is kind of checking whether it opens up or down. If it opens up, is you guys did 4 in class. Gonna do it again? No. Subject to okay, who knows how to do Lagrange multipliers? Anybody?
Yeah, get the general formula. And go from there.
What do you mean by the general formula?
Isn't it just the gradient of f equals and the gradient of g of x? Or, yeah, g.
Yes, exactly. And of course, this guy is g. So what's the gradient of f? I mean, it's this partial x, this partial y, this partial z. Now we have something that's non-trivial, I guess. Gradient of g is 2x, 2y, 2z. So we get 3 equations. We get 2 equals 2 lambda x. How is it already calibrated wrong again? We get this identical equation for y. 2 equals 2 lambda y. X.
Just gonna get worse. Might as well do it again.
And for z, we get 1 equals. I clicked the board once, and it already got screwed up. 1 equals 2 lambda z. So, how do we want to do this? The idea of Lagrange multipliers is set up this system, and then you solve for lambda everywhere. So you got lambda equals 2 over 2x for the first equation. So that's, sorry, we're going to solve for x, y, and z. I like that. So x equals 1 over lambda.
I have a quick question. So we have those 3 equations.
Yep.
And I'm always confused. Is that 4th equation, the subject to, also an equation we can use while solving this? Like, when does that come into play?
After we solve for x, y, and z. We want x in terms of lambda, y in terms of lambda, z in terms of lambda. Then we plug them in here, and we solve for lambda.
Okay.
And then we plug it back in here and we get the answer. So this is also going to be y, right? Because these two equations are the same. Then z is going to be 1 over 2 lambda. So this is going to be 1 over lambda squared. The subject to constraint. We're going to put in 1 over lambda squared, because 1 over lambda is x. 1 over lambda is also y. And 1 over 2 lambda is z. Oops, the square down here. Can I erase? We have 2 of these. 1 for x, 1 for y, and then 1 over 4 lambda squared. Yeah, so this is where our constraint g with the equal sign comes into play. We just solve this for lambda now. So we can say, I'm going to say 8 over 4 lambda squared. So now I have 9 over 4 lambda squared. 9. Doing several steps in my head, I can say 1 equals 4 lambda squared. So lambda equals 1/2. Right? Does everybody follow me here?
Negative though, right? That changes. We have multiple.
Yes. So yeah, plus or minus. And that's going to give us probably our maximum. So we plug in x equals 1 over this, y equals 1 over this, z equals 1 over 2 this. So we get 2, 2, 4, and we get the negative of that. And we want to check what f equals at these 2 points. You guys have that, right? 2x plus 2y plus z. So obviously the positive one's going to be a maximum, and the negative one is going to be a minimum. And both of them are going to be, the maximum will be 12, the minimum will be negative 12. This is always how you're going to do it. You're always going to find equations for x, y, and z using lambda, and then plug them back into g equals whatever number. That's the basic idea.
Shouldn't that last one be a 1?
Which one?
The portion, I'm trying to think, what was it? It was 1 over 2 lambda.
This one was 1 over 2 lambda squared.
Oh, we plugged the 1/2 back into that equation, not the.
We plugged lambda equals 1/2 into f, which is, sorry, we plugged in x equals 1 over lambda, y equals 1 over lambda, z equals 1 over 2 lambda. Ah, you're right, z is 1. Sorry. That's what you were saying, right?
Yeah, that's. I just wanted to make sure that I was plugging it in correctly.
Yes. Yeah. So we get 9 and minus 9 instead of 12 and minus 12. Any other questions? I think that's this whole thing. Yeah, it gives us a whole page for large multipliers. All right, who likes double integrals? Nobody, right? Everybody hates them. Can I erase? 06. E to the x squared. First question. What does the region look like? What is the region of integration? So what does this guy look like? We don't care about any of the actual stuff.
Put it on a coordinate, like a graph and everything, so that would be the domain and range for what you're looking at.
Well, I claim it's obvious that they're positive numbers. That's why I drew this in a weird spot. So this guy corresponds to dx, right? So we're going to have x equals y over 2 to x equals 3. So we know we end at x equals 3, right? X equals 3. But what do we do with x equals y over 2?
So for y.
Yeah, exactly. So for y. So y equals 2x. And we all know what that line looks like, right? So this is the line y equals 2x. And now we can't really do anything with this if we're wrong. But we know that y equals 2x is going to hit 6 at x equals 3, right? So we know that this one will be satisfied, just because of the way this one worked out, which is great. So this is our region. This is our region. Questions? Determine the value of the integral. So, to compute the integral, we don't want to compute this derivative, sorry, this integral, because e to the x squared is actually impossible to compute by hand. The integral of that is impossible to compute by hand. So we don't want to do that. So what do we want to do? Anybody know Fubini's theorem? Fubini's theorem is what?
Prove the name.
It's the really useful one, where you can change this into a double integral over wherever, whatever region you're on. And dA, but A is just, that just means you can do x first or y first. Doesn't make a difference. And actually, I don't want to do x first. But we'll see that in a minute. So I'm going to rewrite this. I can erase it. R e to the x squared y, I'm going to do that first, yes. Okay, now, what's R?
The region we graphed.
Exactly. This is a horrible version of it because the thing is calibrated. But yes, it's the region we graphed. So if we want to do dy first, then what do we if we want to do dy first, what does y need to equal on our bounds of integration? What do we want to put here? Well, we still want it to be this long. This line. We want it to be this line, just like it was before. But let's write it in terms of y. So this time, instead of going from y over 2 to 3, why don't we go from 0 to 2x? Now everybody should try to do that while I recalibrate the screen again. So if this integral is from 0 to 2x, the other one has to be in the x direction. I mean, we're going from 0 to 3. There's not much choice here. So, the first integral, dy. Why is this beautiful?
It's going to be a u substitution here.
Right. The answer I wanted was there is no y. It's super easy, but that's also correct. So the integral of this is just y times e to the x squared from 0 to 2x, which is, I claim it's obvious that it equals this. Does anybody disagree? Does anybody think that this is not obvious? I did the entire integration in my head. I hope everybody's okay with that. Lots of yeses. All right. And now we have a nice use of. What is the use of? I don't want to do it. Or I'll do it, but I don't want to tell you what it is. You know, obviously. Anybody else? What u equals what? What do we want to put in? Du equals 2x dx. Like magic, this becomes. I like to change my bounds here. So some people will just write this as an whatever, this integral of u and then change it back to x. I like to just change my bounds now. So I'm going to go from u equals 0 to u equals 9 of e to the u, because our 2x canceled out, and now we have this, which is incredibly easy because e to the u is magic. And we get e to the u 0 to 9, which is e to the 9 minus e to the 1, e to the 0, which equals 1. So we're done. Did I go too fast? Any questions?
I guess just one of the general questions I've had is that how do you know what direction you're going along the region? Because sometimes in class we've drawn out that we're going horizontally across the region, or sometimes we're going vertically. How is that portrayed by the integrals?
So we got to do both, right? Whenever we do a double integral, it means both directions.
Okay.
It just means the question is what order do we go in?
Mm-hmm.
If we want to go horizontal first and then vertical, that means we want to do dx and then dy.
Okay.
But as I said, that's impossible in this case.
Mm-hmm.
So you pick whichever order is more convenient.
All right. Thank you.
Everybody good? Everyone agrees? Find the volume of the solid. I'm going to erase, unless anybody erases it. I'm going to call this one F and this one G, because I don't want to write them both as C, because that would get confusing. So I'm going to say F equals 2x squared plus 2y squared. And I'm going to say G equals, actually I don't remember, 27 minus x minus y squared. Find the integral of the intersection? What do we call it? The volume of the solid bounded by these guys. Okay. Does anybody have any idea what that looks like? Nope? Okay. So, if you stare at enough of these, you start to notice that this is just like a parabola opening up within 3 dimensions. This is just a parabola opening down within 3 dimensions. This one has the tip at 0. This one has the tip at 27. So what we get is a 3-dimensional version of where this is the origin, this is 27. And you can just rotate this 2 pi, I guess, if you want. In fact, you should. I don't want to try to draw in 3 dimensions because I don't have a good way to erase, and also I'm bad at drawing in 3 dimensions. So I'm going to talk about this as if it's 3-dimensional. which might also be helpful because it's easier to think about things in 2 dimensions. So how do we find this area or volume on how many dimensions you're in? This volume. How do we find this volume?
Well, if it were an area, you'd integrate from wherever the intersection point is, the first one to the second one, and you'd subtract it from the lower one, so upper minus lower.
Exactly. So if it were in 2 dimensions, we'd say integral from this guy to this guy of this guy minus this guy. Exactly. So in 3 dimensions, well, it's basically the same. So where do they intersect? How do we find out where they intersect? We said,
Set them equal.
yeah, we said them equal. 2x squared plus 2y squared equals 27 minus x squared minus y squared. Add these over, get 3's, and we get by 3 x squared plus y squared equals 9. So this is a circle of radius 3. So, yeah. No. Well, anyway, it's a circle with radius. So,
Wouldn't it
it,
3x squared? Like, because you'd be adding the x squared to another side, so that.
I added and then I divided by 3.
Oh, divided by 3, right?
I'm skipping steps because I have very much
no, I
to
just missed that.
So this should look really
They wouldn't improve the door.
this should look like polar coordinates. I'll just give it away.
Okay.
Because that is r squared, right? So we can rewrite f as 2r squared, and we can rewrite g as 27 minus r squared. And now we're kind of in 2 dimensions instead of 3, kind of. But how do you find how do you use polar coordinates to do this? Because it's a little bit tricky. So double integral from 0 to 2. So you go around the whole circle. I'm going to leave this one blank for now. I'm going to leave this blank. And then it's r dr d theta. Everybody remembers that? Everybody knows that? Everybody needs to know that. That's going to be all over the place. Well, now we know we're integrating with r. So where does r go? At this point and at this point, I guess I should draw my z-axis. So r is your distance away from the z-axis, right? So at this point and this point, the radius of, I guess, the radius of this circular cross-section thing is 0 here and 0 here. And it's 3. No. Yeah, what am I doing? Hang on. It's 3 here. Yeah. Yeah. going to be integrating from 0 to 3 of, just like in 2 dimensions, we subtract f, no, sorry, g is on top, f is on the bottom, so we do g minus f, which is 27 minus 3r squared. I'm sure I didn't miss something.
This is. Yeah, I got confused on his approach because he doesn't divide by 3, and I don't get why it doesn't work when you just divide by 3 and go across the integral. Oh, wait. Oh, I see.
Which divide by 3 are you talking about?
I plugged in, sorry, I know what I made my mistake with. I plugged in the equation x squared plus y squared equaled 9 directly into there instead of going through that. Yep.
So this integral, I'm going to have to go to a new page to do. So any questions before I erase? And now, we just do the integral. 27r minus 3r cubed, because I distribute this r. The integral of that, 27r squared over 2 minus 3r 4, 0 to 3. And I'm going to spoil the ending. This 0 to 2 pi is really easy because we don't have a theta, just like we didn't have a y before. We're just going to multiply it at the end. So we have 27 times r squared, which is 3 squared. 27 times 9, happen to know, is 243. Minus 3 times 81, which is 243, over 4. And then this thing is just 243 over 2 times pi. Because we get positive this, then we multiply by 2, so we get 2 in the denominator and pi out. Questions? No? I think that's the end of the practice test. Okay. Any other questions? Anything that I didn't go over, or he didn't go over, or he did, and you want me to go over again?
So number 4, I don't think you went under part 3, which was finding a directional derivative of that.
Okay.
Yeah, you don't have to.
I don't care about the actual question. No. God. Okay, picture.
Actually, the exams are online.
Just this one.
Yeah, this should be on Blackboard. So assume directional derivative is the last part. Otherwise, we would have done it.
So it's the part 3,
Three.
which uses the answer in part 2.
All right, so I guess we're gonna do does part 2 use part 1?
I don't think it says to use part 1.
No. Okay, so we'll do part 2 and part 3.
Nice little guesstimate though.
It also says you can just do it in terms of A and B if you didn't want to do 2. Below 3. If you're unable to get an answer for 2, give your answer for 3 in terms of A and B. It's up to you though.
Let's just do 2. 2 looks easy. Estimate partial f, partial x, 50, 60, 50, 60. So it's going down from 50, 60s, going down from 100 to 90, so negative 10. You guys remember how you estimate, or partial x? Go that way.
I think we just used the coordinates and estimated 50, 60 at that point.
Okay. But if you want to estimate. Nah, I don't feel like doing 2. 2, I'm not sure how he wants you to estimate it. So let's just use A and B or something like that. So, determine the directional derivative at 50, 60. Right, I'm not in the right place. In the direction of the vector 1, 1. Okay. We'll say A equals partial f, partial x, 50, 60, and B equals f sub y at 50, 60. Okay, so do we know how to find a directional derivative? No. Okay. Make sure that I actually know how to do this. Yep.
I'm going to be rude and head out.
Alright.
Just I wanted to go out.
So we always want our directional derivative to be a unit vector, right? Just when in doubt, make things unit vectors. So this guy, we don't actually want to use this. We want to use, right? We want to use v over, what do you call this? Size?
Magnitude.
Magnitude. Magnitude, that's the one. So what is this? I mean, what's the size of this guy? So we get v. The size is root 2, right? Yeah. So we divide by root 2. Is that what you meant? Good. So this is our unit vector. We're going to use this now. And the directional derivative is just, I guess I'll write it as gradient of f dot, right? Better be dot. Yeah, good. Dot, our unit vector. So dot, except we're going to divide the whole thing by the magnitude of v. And we didn't actually find the gradient of f. We're just going to pretend that it's AB. So we get AB, oh my god. A dot 1, 1 over root 2. So, surprise, surprise, A plus B over root 2. In class, we'll probably have estimates of f sub y. So if you plug them in there, you'll get a number. Questions? Does it make sense what the directional derivative is? Yes. Good.
Actually, now I'd like to review what the directional derivative is.
Yeah,
Okay, there you go.
Sure what it was being applied to here.
Can I erase this stuff? Everyone knows how to do this. I have given you the correct definition of directional derivative. So, directional derivative is like asking, what's the derivative that way? Usually you ask what the vector of derivatives is, so you know, like, you want to know your derivative in x, your derivative in y. Here's f sub x, f sub y. But sometimes you want to specifically know what the derivative in this direction is. So you kind of just say, well, it's this proportion f sub x, and it's this proportion f sub y. And the way I've drawn this triangle, I guess, this is like root 3, and this is 1 or something like that, because I drew it funny. So what we're doing is we're saying, okay, I'm going to take root 3 out of the whole thing, which I guess the whole thing now is square root of 4. So I'm going to divide by 2 at the end. Let's just say 1/2 and root here 2. So now this guy is a unit vector. It's because magnitude is 1. So if we want to know the derivative in this direction, we take this kind of percentage in the x direction and this percentage in the y direction, and we add them together. And the way we do that, whenever we add things together, really we're doing a dot product. Let's say Vx, Vy. So if you want to know the derivative of f in the v direction, you do this dot product, which in this picture I've drawn is root 3 over 2 times partial x plus 1/2 over partial y. Does that make any more sense? Cool. Questions? Awesome. Questions about anything else? The practice exam was super short.
If I have a question on a general concept,
Yeah. That's
So-
what this was.
I'm here, I'm just having trouble getting the idea of what that definition is referring to.
The first one or the second one? Oh, the one with question marks, yeah.
It's something simple. Because those are some of the general concepts they want us to go over.
Can I erase this? So, just like in calculus,
Okay,
if we think about this in one dimension, or 2 dimensions, whatever you want to call it, like this.
okay.
For some people it's 1, for some people it's 2. This being differentiable means that this being differentiable at this point means if I scoot along in this direction, I get closer and closer to the correct tangent line, right?
Okay,
Same. If I get closer and closer this direction, I'm approaching the correct tangent line at that point.
oh, that's all that's referring to, is that as you approach that point, you're getting the tangent for a differentiable graph?
Yeah. Except now it's a plane, so you rotate everything. And I guess even better, you just slide everything out of the board, and now you're saying that you have a tangent plane in this direction.
Got it,
It's phrased very strangely there.
got it. Thank you for simplifying it then.
A lot of this class is much easier if you think about it as if it were calculus. Some of it makes no sense. Other general questions? Like I guess that was the study guide that had just like general stuff on it.
The chain rule?
The chain rule. Oh yeah, the chain rule. Okay. That's tricky. So you want to know like z dx, right? There you go. So if we say z equals f of x, y, right? This derivative equals, I hope I get this right. Does anybody know the chain rule? Hopefully somebody knows it well enough to call me on it if I'm wrong. Partial f. This is making sense. I have different units in my head than I should. Okay.
The formula we have is dy dx, but
You have dy dx. Okay. I'll do that one instead. So, dy dx, but this is dy dx, and you still have z equals f of xy.
Yes.
F of x, y. So, this thing, I believe, is I don't know. I don't actually remember the change.
Do you want the textbook? Book is the chain rule?
Aha, I knew it was doing something weird.
I mean, that's only one case.
That's odd. Okay.
One application, chain rule, AYDX.
So this is. Can I see the version you have in your notes? Well, that's dy dx.
So what is z equals f of x, y, and then you changed it to y equals f of u, v. And then
Okay, all right.
partial y.
So I'm going to write the same thing twice. If you said y equals f of uv, right?
Yes.
Dy dx equals f partial u times du dx. I think should be the way it goes. Partial u du dx, yeah. Plus partial f partial v dv dx, where y equals f of uv. So when you take a derivative, you take a partial derivative. Is it clear why partial y partial x would equal this though? So partial x would equal this guy. If we ignore this other term. So partial f partial x equals, let's say this is f of u. The way we do this in Calc 2, Calc 1, I don't remember which, we would say, all right, well, it's the derivative of the outside, which is df partial f partial u times the derivative of the inside, right? Which is du dx.
So you're doing the chain rule on each term then?
Yeah.
Okay.
So when you say something, when you say df of uv dx, you're going to do this, and you're going to add together partial f partial x, partial f of u partial x, and partial f of v partial x, basically. So you get this guy plus partial f partial v dv dx.
So it's just Calc 1 chain rule, but done like in the form of partials.
Right. And then you add them together, which is also straightforward. Now the version of this in the book, which is exactly the same, but I don't mind writing it down again because then you just get to see it more. Z equals f of x, y. Then dz dt equals partial z partial x dx dt plus partial z partial y dy dt. This derivative is on. It's just like this d means something slightly different than this d. Because this d is a derivative you understand. This thing is the sum of the partials, which I think is strange.
Because you can't do a normal derivative on an f of x, y.
Right.
Is there a quick way to determine whether or not a region is a type 1 or type 2?
I don't know what type one is.
It's just this, I don't know if we'll have to categorize any of them, but if it's on there, I don't, you might put it on just a general question.
So I hate him because he just wrote type 1 and type 2. I don't know what that means.
So type 1 is when it goes across x, type 2 is when it goes across y, I think.
So
And that's,
you're talking about when you integrate, right?
Yeah.
So it's like if we want to integrate f. So like this is type 1 and then type
Actually,
2.
it might have been the other way around. But I know.
Okay, that was type 2 and now this is type.
so it's just, yeah, whether or not you're going horizontally or vertically.
First. But it's always for a double.
For, only for double, yeah. Okay. What's the difference between an iterated integral and a double integral? Because apparently there is a difference.
Yes, there is a difference. A double integral, if I put numbers here, then I can flip these around all I want.
Okay.
I can make it type 1 or type 2 to
Yeah.
use the words that we just talked about. I can do whatever I want there. But if this thing is x, then I cannot do this. I can't do, say, integral 0 to 1, integral 0 to x of f dx dy. I cannot have them in this one.
Right, because you would have to have a y equaling the integrated value of 0 to x.
Right. That's why this is iterated, because you have to do the y first. You can't choose a order,
Okay.
which is Fubini's theorem takes an iterated integral and turns it into a double integral.
Okay.
That's why it's so nice. And now I'm just drawing lines.
Can we do a limit? I know that,
That's a vague question. Okay. Do you have any example?
Do you want me to pull up WebAssign on my iPad and just look one up?
Limit as x Oh my god, I hate this. Yeah, I'll do a limit in a minute. Hang on. Limit x, y goes to 0, 0, 0 of, I don't know.
Oh yeah, you went over those in class. You said we needed to know that.
Specifically this one?
Not specifically that,
Okay.
but cases like this where the denominator may or may not reach 0 as fast as the numerator.
Aha! Exactly. That's why I picked this one.
And why
I picked this one
both
because it's one of the annoying tricky ones. So, if you approach along the line x equals 0, right? Because you have to pick some direction to approach from. So let's approach from x equals 0. That gives us the limit as y goes to 0 of 0 plus y squared over x plus y. Which is y squared over y equals y. So the limit of y, what's this limit?
is 0.
Yes. Yep. I love it when people think it's a trick question. Now, if you approach from along the line y equals 0, well, obviously you get the exact same thing, right?
Mhm.
But if you approach along the line
Y equals x.
y equals x, this does break there, right?
You'd have
No,
2x squared over 2x.
I did it wrong. I want these on the bottom, I think. Right?
X over 2x, right?
No. Crap, I can't remember how to do it right.
You know what that limits?
Yeah, there's some fun and tricky ones. Turns out I gave you one that was okay. I think the limit of that first thing I wrote down was.
You're right. That would approach 2x over 2x squared, which would be 1/2. If you approach y equals x.
It would not be 1/2, it would be infinity. Because you'd still have an x, you'd have an extra x on the bottom, and you're going to 0.
Well, yeah, but like if it's y as the limit of approaches y equals x, and you have x over x squared, you can have that be 1/2, as they said in class.
I
think.
So what if I do,
Because if it were 1/2, then it wouldn't exist.
right, I mean, that's,
Then I think this example might be it. Like this is a type of it.
oh, you use multiplying. Yeah, this is a good example. This is the kind of example I was trying to do. Xy squared over, x to the whole squared plus y to the 8th. So, what people tend to do is they try x equals 0. And they say, all right, well, that's 0 on top, and it obviously goes to 0 on the bottom. Okay, sure. No, wait. If we approach the line, y, x equals 0. Yeah, we get 0 over y. If we approach along the line y equals 0, we get 0 again. And then the next thing to try is x equals y. I think you get something funky there. If you say x equals y, you get x to the 5th on top, and x squared plus x to the 8th on the bottom. Well, it's not clear what that means. Let's try. So you know how
X equals y to the 4.
that's going to be the one that we use to break it. If we do this one along the line x equals 0, you see how this limit will be 0, right? Because the top goes to 0 and the bottom will, the top is 0 everywhere. Then the bottom will slowly go to 0, so the limit is just 0. Same thing happens along this line. But if you try this, the curve, this curve, then you get x times x, because y to the 4th is x, over x squared plus x squared. And this time, the x squareds cancel out, and you get that the limit is half. So that's how you know it doesn't exist. Now, will you have to decide whether a limit does exist? Because I don't ever being asked, show that the limit does exist. Only being asked, show
The
that it does.
millions of possibilities, the different approaches you would have to take.
So then what's a good way to, is it just kind of intuition, knowing what you need to use to make it not work?
Yeah, typically it'll be something like this, and you'll say, well, okay, I want this to be the same as this. And if those are the same, do these become the same? And the answer is yes. And when the top and bottom are the same, you always get 1 over like a half. It's usually a half is the case of it. That's number 2 during the session. Fantastic.
Didn't miss too much, right?
I mean, Matt has been joining and leaving the whole time.
Okay.
And I don't know if it's the same Matt and if the program just decided it's Matt number 2 now for no reason. You want to talk about the contour map?
I mean, we went through it in class and just, I guess, getting used to viewing the 3-dimensional shapes and the 2-dimensional setup. It's kind of confusing because in these cases, we were drawing out the level curves of the contour map when it's being limited by. It makes sense how we did it. I'm just trying to see how I could generalize it.
So a contour map I'm going to draw the worst paraboid ever. Okay? So don't do that. That was an obviously. Can you tell me what the level curves of this guy look like? This is the approach.
Okay. So, if that's,
So, sort of. It can be. Here's the thing. A level curve is just an arbitrary decision of, let's slice it with a plane here. And that'll give us, well, because I drew a paraboloid, I'm going to assume that it's a circular paraboloid. And I'm going to say, slicing it with this plane gives me this circle.
Okay.
Okay, now let me slice it with this plane.
This is like looking down on it from a bird's eye view.
Yes. So from a bird's eye view, plus each one you're just slicing a piece of the function. So this will be a smaller circle. This. And if I sliced it down here, that'd be a bigger circle. So I don't know which is more helpful, the bird's eye view or the slicing it with stuff. But
So on here, this would be as if I was looking down on the saddle.
yes,
Got it.
right.
That's what was confusing.
Yeah, it's like normally you draw your axis like this, right? And this is like X, Y, and Z or something like that.
Mhm.
For level curves, you're pointing the Z axis at yourself.
Yep.
And then you can't see how Z changes. So instead you say, all right, well, let me draw and say, well, Z equals, I don't know, 10 along that shape.
Yeah.
So then you can look at the shapes and kind of figure out what kind of mountain it looks like. Where this direction is up.
No, that actually makes a lot more sense, especially for the fourth question where we were looking at the different altitudes.
Right. You must not go hiking very much.
I know, like I'm a backpacker, so this is the part
I'm
that's
more of
intuitive,
a,
yeah.
I'm more of a forest preserve path kind of, not the hike.
Yeah.
Is there anything I didn't highlight in here?
that there's some level curves.
Oh, only kind of.
Artistic representation.
Thanks for coming, guys.
Thanks for having us.
Crap.
What do you have to
I
do?
think somebody came in and I didn't give them the sheet. Wait, were you last? I was last. Oh, awesome. Amazing. Fantastic.
I'm just going to quickly look at WebAssign real fast and see if there's anything else. When doing the iterated integrals, that's directly calculating the volume, or can it also be the area of the shape that you've ended up cutting out of there?
You'll never use a double integral or an iterated integral for an area.
Okay.
An area is going to be a single integral.
It would be a single integral. So in any cases, we're always going to be calculating volume. Okay.
Yeah.
What would be the transformation equation for it's sent to polar coordinates, from rectangular to polar coordinates? Is that just generally looking at the graph and changing the coordinates?
Yes.
Awesome. Because I know that when it looks like a circle, then you would just use r theta instead of the
R phi theta.
r phi theta?
I mean, that's the one that you're trying to avoid.
Oh,
Nice polar coordinates are, this is Z, R is your distance from Z, so like R equals something, or something bigger. On annoying polar coordinates are R is your distance from the origin, and then theta is your angle around here, and then phi is your angle from the perpendicular.
We didn't even talk about that.
Awesome!
So I'm gonna.
We can
not-
avoid that.
Yeah.
We will never mention it again.
Yeah, so polar coordinates just mean x equals r cosine theta.
Awesome. Good. That's much easier.
No, I think that covers everything, aside from just going over and over the test again.
Yep.
If I come up with anything, I'll probably stop at the arc and might look back over about the sign or something.
Okay, I won't be there, but someone will be.
Someone else?
Thanks for coming, guys.
Someone has to make sense of this.